Okay, so welcome everyone to today's lab assignment. So today we'll be doing the second assignment, and this is the file that the coordinator has posted on Canvas. We're gonna go through all the instructions and complete this file. Okay, so the goal of today's assignment is to determine whether a system of linear equations has a solution, how to reduce the system to a row echelon form, and how to visualize the solution. Okay. So the first thing to do is to create a MATLAB script and save it as lab02.m. Okay, so I have already done that. Here we got the file lab02.m. Okay, so today we'll be getting through a lot of commands from MATLAB, like the magic one, the RREF, the rank, the transpose, the plots, figure, hold on, grid out, subplot, mesh grid, sub, and view. Okay. So this is the reminders about the grading software that you should be already familiar with from the first assignment. So I'm just gonna skip this. Okay, let's dive right into the task. So the first one, create a 5 by 5 matrix A using the magic command. Type help magic in the command line to learn about the magic command. Okay, so first of all, I'm going to start with the CLC command so that it will clear the command screen whenever I rerun this script. Okay, so let's see what this magic command will create by typing help magic into the MATLAB script. Okay, so let's run this. So you should see in the command window, magic n is an n by n matrix constructed from the integers from 1 through n squared with equal row, column, and diagonal sums. Produces valid magic squares for all value of n except when n is 2. Okay, so actually in order to use this command, you only need to put the command magic and include that with a number that is not 2. Okay, so here we need a 5 by 5 matrix A. So I'm gonna use the command A equals to magic of 5. Okay, let's see what it will return. Right. Oh, I wanted to show. Okay, so this is the magic A. So you can see all the numbers are from 1 to 25. Where's 25? Yeah, here. All the numbers are from 1 to 25, and according to the description, the sum of all the entries in the row, the column, or the diagonal are equal to each other. So you can check that the sum of 17, 24, 1, 8, and 15 is equal to 23 plus 5 plus 7 plus 14 plus 16, and so on. Okay, so this is what this command will give us. Okay, that is the first task. The second task is to create a column vector B with entries 1, 2, 3, -1, and 4. Okay, so let's put on matrix. Okay, so in order to put a matrix, a column vector in MATLAB, we're going to use the brackets, right? And inside would be the entries. Okay, so here we got. Okay, so here we need to create a column vectors. So each entry will lie on a row, and each time you want to create another row, you would need to use the semicolon, right? So we should have 1 semicolon, 2 semicolon, 3 semicolon, -1. Okay, so here we got a column vector 1, 2, 3, -1, 4. Okay, so that is the second task. Moving on, create a matrix M by augmenting the matrix A with the vector B. So if you want to augment these two matrices together, simply put those matrices inside a bracket. So there are two types of augmentation of matrix. The first one is to put the second matrix on the right-hand side of the first matrix. And the second type is to put the second matrix below the first matrix. So here we are trying to solve the linear system of equations. So we are putting the second matrix on the right of the first matrix, right? So in order to do that, simply put these matrices together without a semicolon in between. Because if you include the semicolon in between, it will add the second matrix in the bottom of the first matrix. Okay, so let's see. Okay, so as you can see here, this column here is actually the column of vector B, and all the other columns are from vector A. So this is the matrix F. Okay, so that's task number 3. Task number 4, check the rank of matrix A and matrix M using the rank command. Type have rank in the command line to learn about the rank command. Okay, so first of all, let's type in have rank to see. Oh, sorry. Have rank to see what it will return. Okay, so rank, matrix rank. So rank of A provides an estimate of the number of linearly independent rows of all columns of a matrix A. And also we got another command like rank A tall, but we're not going to use this. Okay, so here basically the rank of A will return the rank of matrix A. So in the lectures next week, we will talk about the linearly independence of vectors. So actually the rank will be determined on the number of linearly independent rows of vectors, but we will discuss that next week. So for now, in order to determine the rank of these matrices, simply use the command rank of the matrix. Okay, so we need two variable rank A and rank M here. So rank A is equal to rank of A. Oh, I'm sorry. And we would have the same things for matrix M, but let's just change. Okay, let's run. So as you can see on the screen, rank of A and rank of M are both 5. Okay. So you got a question here, is the system with augmented matrix A consistent? So remember, if a system of linear equation is called consistent if there is at least one solution. And so in order to answer this question, you need to consider whether this system of linear equation has any solution or not. Okay, so as you can see here, oh, let's get back to the matrix M first. Let's show the matrix A and matrix M. So this is the matrix A. It is a 5 by 5 matrix. This is the matrix M. It is a 5 by 6 matrix because we are adding one column from the vector B. Okay. So the row of matrix A is 5, and the row of matrix M is also 5. Oh, I'm sorry, the rank of matrix A and the rank of matrix M are all 5. So remember, we have previously discussed about the rank of matrix. Actually, the rank of a matrix is the number of leading entries in its row echelon form, the row echelon form of the matrix. How many leading entries you have in the row echelon form, it will determine the rank of the matrix. Okay, so because the rank of these matrices are 5, meaning that the row echelon form of the matrix A or M will have 5 leading entries. Okay, and remember, we talk about the pivot columns. Okay, the pivot columns of the matrix is actually the columns that contain one leading entry. Okay, so because we got 5 leading entries, so 5 of the columns are pivot columns. Okay, so because the size of A is 5 by 5 and all the columns are pivot columns. So this is equivalent to saying that this system of linear equation has a unique solution. Okay, so the answer to that is the answer to question 1. You can put your answer in. Okay, so that is task number 4. Okay, so now let's get to task number 5. Produce a reduced row echelon form of n by using the RREF command. Type help RREF to know more about this command. Okay, so help RREF. So actually RREF stands for reduced row echelon form. Okay, so let's see. So RREF uses the given tolerance in the RREF stands for reduced row echelon form. So RREF A produces the reduced row echelon form of A. So there are several commands related to this RREF, but now we only need the first command. So I'm going to use this one. Okay. So the variable name will be RREF. RREF. M is equal to RREF of M. Let's see. Okay, so this is the RREF of right. This is the RREF of M. Okay, so I can clear this now. Next, create a 7 by 7 matrix C using the run command. Type help run in the command line to learn more about the run command. Okay, so we are getting into another section. So I'm going to skip a line over here. So help. So here run is actually stands for random. Okay, uniformly distributed pseudo-random numbers. So if you put R equals to random of n, it will return an n by n matrix containing pseudo-random values drawn from the standard uniform distribution on the open interval from 0 to 1. Okay, so meaning that when you put random of n, it will return an n by n matrix where the entries are chosen randomly in the interval from 0 to 1. Okay, so let's try to put random of 7 because we need a 7 by 7 matrix. Okay, so C is equal to rand of 7 and run. Okay, so here as you can see, we got a 7 by 7. 1, 2, 3, yeah, 7 by 7 matrix C, and all the numbers are from 0 to 1. And they are chosen randomly, but in a uniform way. Okay, so that's what this command will create. So let's clear this now. Oh, I'm sorry. Next, let's talk about 7. Create a row vector D with 7 elements using the run command. Okay. Oh, sorry, but now we need to see how to create a row vector using the run command. Okay, so now we need a row vector with 7 elements. So actually it is a 1 by 7 matrix, right? It is a 1 by 7 matrix. So now actually we will need to use this command, run of M and N. It will return an n by n matrix. And once again, we need a 1 by 7. So m is going to be 1 and n is going to be 7. And the entries will be the same, chosen randomly in the interval from 0 to 1. Okay, so let's put on D equals to rand of 1, 7 and run. Okay, so this is D. 1, 2, 3, 4, 5, 6, 7, right? And all the numbers are chosen uniformly from the interval from 0 to 1. Okay, so we can clear this now. That is task number 7. Task number 8, apply the transpose to command to D. Type help transpose in the command line to learn about the transpose command. Okay, so actually from the name, you can easily tell that it will return transpose of the matrix, but let's follow the instruction and type in help transpose. Right. So if you put B equal transpose of A, this is called, okay, so another way to create a transpose of a matrix is using this command, dot, and this one over here, this symbol over here. It is equivalent to using the command transpose of matrix A. Okay, so simply we need the variable transpose D. I'm gonna put transpose D equals to transpose of D. And let's work. Okay, so now transpose D is a column because originally D is a row vector. So if you have taken the transpose, you will have a column vector. So what does the transpose command do? Yeah, actually it returns the transpose of the matrix. Okay, that's number 8. Task number 9, create an augmented matrix N of the system with coefficient matrix C and right hand inside D. So we did it before, so we're gonna do something like this, but with C and D. Okay, so what's the name? N. N is bracket C and D. Okay, let's work. Oh, I'm sorry. It should be, okay, so here D is a 1/7 matrix, which is a row vector. So in order to augment C and D, actually I had to put transpose D instead of D. So that's the reason why when I put C and D, it got a problem. Okay, so fix that, and you should have this augmented matrix over here. So that is matrix N. And next, we need to create the reduced row echelon form of matrix N. So similarly, RREF N is equal to RREF of N. So this is the reduced row echelon form of N. Okay. Next. Okay, so here we got another section. Let's keep a line. So task 11, consider the system of these two equations. So x plus y equals 3 and x minus y equals 0. Plot the lines representing each of the equation on one graph using the plot command. On the interval from 0 to 5, use the color red for the first equation and the color blue for the second. Okay, so first of all, the coordinator asks us to put all of this command in. So I'm just going to copy all of that. Okay, so first of all, we need a figure. Next, x 0, 0.1. Okay, so we talked about this command on the first assignment already. So actually it will create a row vector started with 0, ends with 5, and all the entries will be 0.5 apart from each other. Okay, so basically 0, 0.1, 0.2 up until 5. That is x. Next, we got y1 equals to 3 minus 2 to x. And y2 is equal to x. And we are going to use plot. So x, y1, and then red. Sorry. Okay, to plot these two functions on the same graph, you need to use the command hold on. Hold on. And then plot another one. So this time x, y2, but now blue. And Finally, grid on. Okay, so let's run. So as you can see, there's a problem. Invalid expression, check for missing multiplication operator. Okay, so this is the problem. So actually the problem is here. As you can see, they got a red underline on the X here. What is the problem? So as you can see here, X is a vector. So when you are putting 2X, meaning that you are putting a scalar multiplication. You are multiplying a scalar with a vector. So in order to do that, you need to put the multiplication operator here, which is the star. Okay, so after I have put the star here and I rerun, everything is fine. And as you can see, they will open a separate window, and this is called figure number 1. And the red one is the graph of the first equation, and the blue one is the graph of the second equation. Okay, so this is basically what all of these commands will do. Now let's get to the question. So what does the figure command do? What does the plot command do? What does the hold on command do? What does the grid on command do? What if we type in grid off? What will happen? Does the system have a solution? Okay, so you can answer all of these questions simply using the help command from MATLAB. Simply type in help and the command. But I will give you a hint. So actually this figure command here will create a separate window called figure like you just see on the screen. The plot command will, just like the name, plot the graph of the function you put in. Then hold on, helping you to plot two graphs on the same figure. If you don't use this hold on command, it will return two separate windows with two separate figures. Okay. And grid on meaning that you will turn on the grid. Grid off means that you will turn off the grid. Okay. And does the system have a solution? Okay. So in order to know whether the system has a solution or not, you need to check whether there is an intersection between these two graphs, right? So as you can see, there's a unique intersection between the red line and the blue line. So the answer is yes. And to be more specific, the solution is unique. Okay, and if you put, okay, so as you can see here, the intersection, the coordinate of the intersection is x equals 1, y equals 1. So that is actually the solution to this system of linear equation. Okay, so that is all. You can put your answer into the file now. Okay. Next, task number 12. Okay, so here we would do the same, but here we got a system of free variable. We got a system of free variable. Consider a system. Note that this system is corresponding to the following augmented matrix P. Now you need to type in all of these commands. Okay, so simply it is similar to these commands, but because previously we only have x and y, so we will consider y as the function and x as the variable. Now we got x, y, and z, so we will consider x and y as the variable and z as the function in terms of x and y. That's why there is a slight change in the command. Okay, let's put on all of these. Once again, figure. Okay, so because now both x and y are variable, you will need to use the mesh grid. I think we talked about this on the first lab assignment already, so you can check that. So here, similarly, x is from -5 to 5, and all the coordinate of x out 0.1 apart from each other. Similarly, it is the same for y. I forgot number 1 here. That is x. Okay, so z1 equals to 1 minus 2 star x minus y. Okay. Z2 equals to -x plus y negative 1. D3 equals to, where was that? 3 star x plus 2 star y minus 6. Okay, so these are the free function from the corresponding free equation. Next, we need, hold on. Oh, so sorry, we need the sub one first. So basically the sub command is similar to the plot command, but because we are working with 3D graphics, so we need to use sub instead of plot. Okay, so sub x, y, z1. Hold on, the same things happen here. Sub, sorry, x, y, z2. Then hold on once again. And last but not least, sub x, y, z. Okay. Now let's run. Okay, so this is the figure. So as you can see, each of these functions, the graph of this equation will be a plane, right? So as you can see, we've got 3 planes in this figure. Okay. So what does a mesh grid command do? What does the sub command do? Yeah, you can type help mesh grid and type help sub, and you should be able to answer this question. Okay, let's get to the final task of today's assignment. Come up with 3 systems of linear equations in 3 variables with 3 equations each, representing all possible situations. No solution, a unique solution, infinitely many solutions. For each system of equation, create a corresponding augmented matrix. Okay, for each system of equation, create a corresponding augmented matrix, respectively naming them no solution, unique solution, infinitely many solutions. Apply the commands above to produce a visual picture of each of the systems, each on a separate figure. Use appropriate limits for variable x and y and command view to present each case clearly. Okay, so that's a lot to do. So first thing to do is to think of 3 system of linear equation representing the case where the solution does not exist, the solution is unique, and there are many solutions. Okay. Okay, so I think I'm gonna start with the no solution first. Okay, so in order to create a system of linear equations such that there is no solution, just create a system such that there are 2 equations that is completely wrong when you put them together. Like for example, if I have x plus y equals 1, and then I got x, let's have x plus y plus z equals 1, and then x plus y plus z equals 2. So obviously, if you put this equation together, automatically 1 is equal to 2. And that is impossible. So obviously, if you use these 2 equations, the system will automatically have no solution. So for the third equation, I will put something randomly like maybe 2x plus z equals 0 because I like that. Okay. So this is my system. You can think of your system if you change all the coefficients. Okay. So the first thing to do is to create create the corresponding augmented matrix, respectively naming them no solution, unique solution, infinite solution. So we are in the case of no solution, okay? So no solution is a matrix. Okay, so the first row, the entries would be 1, 1, 1, 1. right? So 1, 1, 1, 1. Then the next row, it should be 1, 1, 1, 2. 1, 1, 1, 2. And the last row, it should be 2, 0, 1, 0. 2, 0, 1, 0. Okay, so let's check if we have the correct matrix here. Okay, so 1, 1, 1, 1, 1, 1, 1, 2, 2, 0, 1, 0. Okay. For now, let's. Yeah.
Is it to create just 4x4 matrix or
Oh, this is a 3x4 matrix. Yeah, so what's your question?
I'm wondering if MATLAB is going to consider that just a regular 3x4 matrix or 3x3 by 3x1.
Yeah, as you can see, there is no vertical line, so MATLAB is going to treat this as a regular 3x4 matrix. Okay, so that's how MATLAB works. But we don't really need to care about that, whether there is a vertical line here or not, because it is still going to work. So that is the no solution matrix. Next, apply the command above to produce a visual picture for each of the system. So I'm just going to copy all of this and change the coefficients because I'm lazy. Okay, so for the first case, we got z is equal to -x, -y plus 1. So it should be -x, -1, and then plus 1. For z2, it should be -x, -y, but plus 2. And for the final one, it should be -2 multiply x. And that's it. Oh, sorry. What is the delete button? Okay. Yeah, and run. So this is, oh, what happened? Continue. Run. So what happened? I think we need the instruction email. Let's just open this file. What is this? Okay, what happened here?
You have to put the y in 0 times y. That's
I think it is not necessary, but if you put that command. Oh, okay. So, okay, so okay, let's put on 0 divide y, just like he said. Okay, so we need to include this because without that, it won't be able to. Okay, so as you can see here, because we are taking the value of x and y from -5 to 5, it makes the plane is pretty flat and hard to see, hard to watch. So I'm just gonna reduce this to something smaller, like maybe from 82 to 2, to see whether it's gonna be easier for us to watch the results. Okay, run. Yeah, it is better. You can, yeah. So as you can see, Oh, so you can use your mouse to switch the view. But as you can see, these two planes are parallel to each other. These two planes are parallel to each other. And the third plane, it intersects with the first plane. It intersects with the second plane, but there are no common points between all of these three planes. So that's why the system of linear equation does not have a solution. Okay. So basically, I have finished all the tests, even though you still need to create something like this, but for the other two cases. Okay. And so you can also use the command view to change the view of the figure, but I think I'm just gonna stick with the default. Okay, so if you want to learn more about the view command, you can type in here, help view, and this is it. Okay, so view, set the angle of the view from which an observer sees the current 3D plot. Okay, so yeah, you can change the view from which the observer will see the plot, but for now, I think we're just gonna stick with the default, okay? So yeah. Yeah, so basically that is the lab assignment for today. You still need to create one more matrix for the unique solution case and one more matrix for the infinitely many solution case. Okay, so for the case of infinitely many solutions, simply using the same equation for those three equation in the system, and in that case, all the planes will coincide with each other, and that will guarantee you will have infinitely many solutions. Okay. Yeah, so do you guys have any question? Okay, that's